Okay, so another example of a quadratic equation where we have to set it up is a common physics example of a free-falling object. So this is a basic example of a free-falling object where we're going to ignore some stuff. We're just assume the only thing at play is gravity. There's no air resistance, wind resistance, surface resistance, or friction. We're going to assume only gravity is the force after the ball's been launched or after object's been launched. Gravity is the only thing pulling on it. Alright, so an example of a free-falling object where it's been launched into the air and we're only assuming gravity is at play is this physics equation, this physics quadratic equation, where s of t equals negative 16t squared plus v naught times t plus h naught. And what the s of t function calculates is the height the object is above the ground, above the earth, t seconds after it's been launched. H naught represents where it was when it was launched. The initial height at time 0, this is where the object was launched from. V naught represents the initial velocity. At the time it was launched at a velocity of whatever that V naught is. And velocity is speed and direction, so velocity can be positive or negative. The number, like 10 feet per second, that would be a velocity moving in the positive direction. Its speed is 10 and it's moving in the positive direction would be up or to the right. Negative 10 with a velocity would mean its speed is 10. Negative just says it's approaching the ground, it's coming towards the ground, or it's moving in the leftward direction. Alright, so again, that's the velocity, speed, and direction. So we're going to do an example of a baseball player hitting a baseball. Alright, so suppose a baseball player hits a ball. Alright, so we can use our formula because we're assuming once he hits the ball, he's launching it up into the air, and it follows a parabolic pattern. It goes up and then comes back down to the earth because the gravity is pulling it back down to the earth. But it's going to go up for a little while because, again, like I said, it's been hit hard and launched into the air. So suppose that we've clocked it when the baseball player hits the ball with his bat, he launches the ball into the air at a speed, a velocity, of 80 feet per second. When he hits the ball, his bat is approximately 3 feet above the ground. So there's sort of the picture here it's giving you. It connects with the ball, it launches it up, and its speed, that moment when it hits the ball, the speed is 80 feet per second, and the bat is 3 feet above the ground. And so there's my initial velocity and my initial height. And so my equation that models the height of the baseball after t seconds, once it's been hit, is negative 16t squared plus my initial velocity times t plus my initial height, which we know what those are. 16t squared. The 16t squared is has to do with the pull of gravity. V naught was 80 feet per second. H naught was 3 feet. And so there is the equation, as long as the only thing at play is gravity, that will tell me how high the ball is above the earth at any time during its flight. Alright, so again, t represents the time in seconds the ball is in the air. And s of t is the height above the ground in feet during that time. Alright, so there's A. There's answer to question A. Question B, which is actually down here below the picture. And then we'll get to question C. Alright, how high is the baseball 2 seconds after it's been hit? And then find the maximum height of the baseball. Support your answer graphically. So we'll find the maximum height by hand, and then we'll look and check and make sure it works graphically. Alright, so first, so part B, we want to know how high it is after 2 seconds. So we're going to plug 2 into my equation. So s of 2, so negative 16 times 2 squared plus 80 times 2 plus 3 comes out to be 99. So after 2 seconds, the ball is 99 feet above the earth, the ground, earth, however you want to say it. Alright, now the maximum. Alright, so remember, it's going to go up and come down, so we do have a maximum height that's going to occur at the vertex. And so I've got to find the vertex. The maximum is the vertex. And so we find the vertex by finding the t value, which is the x value. It's the opposite of b over 2a. Alright, so opposite of b was 80, so opposite of 80 is negative 80. Over 2 times a was negative 16. So if I take negative 80 divided by negative 2 times 16, it comes out 2.5 seconds. Alright, so it shouldn't be much higher than 99, right? It hits 99 feet after 2 seconds. And so it's only going to travel upward a little bit more for half a second more. Alright, so the maximum height should be close to 99, a little bit higher, but close to it. After 2.5 seconds is when it's going to come back down to the earth. Alright, it's reached its peak, and now it's going to arc back down to the earth. And so to figure out, well, this is how long it takes, but the maximum height is actually taking that and plug it into the equation. So the maximum height the ball achieved is taking my equation and plugging 2.5 in. So I'll go back up here and plug 2.5 in. So I take negative 16 times 2.5 squared plus 80 times 2.5 plus 3. And when it's all said and done, it comes out to 103 feet. Alright, so the ball reaches its peak after 2.5 seconds. That peak is 103 feet above the earth. Alright, that's its peak. Alright, now to check it graphically. Well, I go to my graphing calculator. I go to my graphing calculator, and I think I already have it typed in. Negative 16x, I'm going to double check. Negative 16x squared plus 80x plus 3. I'm going to go to my window to explain the window that I needed. Alright, so this was the window. I like to make sure I can see my axes, so I made my x minimum. Negatives don't make sense, right? Because I can't have negative time and I can't have negative distance. But I put the negatives in there so I could see the x-axis and I could see the y-axis. So you could make those zeros if you wanted to. My x max is 10 because I'm assuming the flight of the ball will be less than 10 seconds, right? When you if you watch a baseball game and they hit a baseball, it's much less than 10 seconds. The ball isn't in the air longer than 10 seconds. And then the y values represent the height, right? And I know the maximum height is 103. So in order to see my picture, I went to 110, right? You could go to 103, but then it's on the edge of your graph. I like to go a little beyond so I could see it. And then I scaled by 10 here so that I only have 11 dash marks versus 110 dash marks. All right, hit graph, and there's the path of the ball. So the ball is initially launched up. It goes up, it arcs up. After 2.5 seconds is when it reaches this peak. And then it arcs down. All right, and I'm going to check that it's its peak. Now, you could go through and find the maximum key on the calculator if you want to. I'm just going to check my answer by plugging it in. So I'm going to hit... Actually, maybe I'll walk you through it because it's just a good idea to go you through. So finding the maximum if we're trying on the calculator. So second trace, remember, second trace is where we do math on the graph. The fourth one down is maximum, so I hit 4, and then the calculator asks you to do some work. So it asks you to go to the left of it. Make sure you go to the left of it. So you go beyond. So it looks like my peak's around there. So I want to make sure I got good to the left of it. Hit enter. And then I go to the right. Hit enter, and then you can guess. Hit enter. Alright, now, I'm glad I did this because it shows you that the calculator is flawed, like the last time. Again, the program goes back and forth, back and forth, back and forth until it hits a maximum. Because the program, there are errors involved, because it's not perfect. And so you'll notice here that it came out 2.499997. Now my y was 103, but this really should be 2.5. Right? And again, it would logically make sense to round that to 2.5, and I can check the answer. Second trace, hit value, type in 2.5, and there it goes, it puts it up at 103. All right, so 2.5 is the correct answer. Right, that's when we reach our peak. Alright, so when we look at our graph, so remember this is time in seconds, this is the height in feet. We start at 0, right? Only the first quadrant makes sense. We can't have negative time and we can't have negative distance, so we start here at 0. If we plug 0 in, remember it starts at 3 feet, so it starts here at 3 feet, goes up, peaks, and then comes back down, and then this is the moment where it would be hit 0. And that's when it would hit the ground. there's the path, there's the time, there's the ball is in the air over that time period, over that piece of my parabola. We know what the maximum is. That occurs at 2.5, which would be the axis of symmetry, and 103 feet is the maximum. Alright, so for the first 2.5 seconds it's arcing up, hits the maximum of 103 feet, and then after that it declines back down until it hits the earth. When it hits the earth, it's at a height of 0, right? Hits the ground, S is 0, my height is 0, 0 feet above the ground when it hits the ground. I actually need to find that to get to my next answer. Alright, the next question, if you remember, is estimate the domain and range. And it's estimate the domain and range in context. That's why it's estimate. If we were looking originally at the entire function, the domain would be all real numbers, and the range would be everything from 103 to negative infinity. But that doesn't make sense in an application because negative values aren't allowed. Time cannot be negative, and distance cannot be negative. And so when I do my domain and range, I've got to keep in mind that they can only be positive values. And so that's why the picture is helpful. We want to draw the picture. And so to do part C, my domain, again, is time. Well, time can only be positive. So I start at 0, and then it only makes sense, this is where it's going to stop, at this 0, because I don't go past the ground, right? And so I have to figure out what this time is when it comes back to the earth, because that's the entire flight of the ball, and that's what the domain represents. This is the time the ball is in the air. And so to find that, well, I'm going to use my calculator to find that 0. So I'm going to go back to my calculator. Remember, it's under second trace, so I go back in here, second trace. I'm finding my 0, which is 2. And then it's going to ask me to do some stuff. It's going to make sure I stay to the left. And so the left are going to be a positive value. So I make sure I stay, my y values I'm looking at, make sure they stay positive. Alright, so that looks pretty close, positive 1.29. Hit enter. And then I want to go to the right, which means I want to go negative. And so there's my first negative value. Hit enter. I don't usually move it for the guess. I'm just going to hit it. And so it hits 0 at about 5.37 seconds. 5.037, sorry, I think I said that wrong. And since it's an estimate, I'm going to go ahead and round that to 5 seconds. So the ball is in the air for 5 seconds. From the moment it's hit, maxes out at 2.5, and then comes back down to the earth in 5 seconds. Alright, so the domain is 0 to 5. My range would be the heights it reaches. Well, this also is important for the range. That would be a height of 0, right? When it hits the ground, it is 0 feet above the ground. And it can do that, right? It comes all the way down and hits the ground, as long as nobody catches it. I'm assuming nobody catches it. And so the range starts at 0, and then its path has a maximum of 103. And so the ball travels for 5 seconds, hits a maximum height of 103, and a minimum height of 0. Right, it hits the maximum at 2.5 seconds, and the minimum after about 5 seconds, a little over 5 seconds. Right, and that's the path of the ball. There's the domain and range. And so that's as simple a physics as the end. If you take a physics class, you do a lot of these free-falling objects. We'll do more later on. And so that's just another example of where we can set up a parabola, and we have to solve for max, mins, and zeros. Next examples are going to be a little simpler because we'll be given the equations form, but we will still do later on in later sections one where we'll have to set up. So we'll do more later on where we'll have to come up with equations. But the next example, which I'm going to do in my next video, are going to be cases where we'll be given our quadratic.